All right. Good afternoon, everybody. Thanks for coming. It's been said that a programming language is a tool, and that different tools are designed to be good for different tasks. What is C++ good for? Is it a different sort of tool than other popular languages? And if so, how so, and why? How did that arise? This talk will go into some depth on the legacy of C++, especially what we share with and inherited from C. There's some very novel things that come from the way that we share an ecosystem, but changed language rules.
We also want to talk about what the design priorities of C++ are, both today, but also in the future. What is it about C++ that sets it apart from other programming languages? What makes it a unique language, a unique tool that we can use to solve particularly interesting problems? And also, in what ways do those differences actually turn into challenges when programmers are using it? What sharp edges emerge because of the ways C++ is different from your other programming language tools?
But we aren't going to actually do any deep comparison with other languages. This isn't a we're better or worse. And I certainly don't know any other languages nearly to the same extent that I know this one. But we can explain in, I think, a lot of depth what C++ really is. And for that, we need to start with a semi-serious question. What programming language is best? Fundamentally.
Any theories, really?
Any guesses? Yeah. A lot of trolls in the audience.
Yeah.
Which is great. It's fine. It's Friday afternoon. Let's do it.
Yeah.
So what do we mean by best? What goes into best? There's a lot of things that we could be individually optimizing for when we decide what language might be best. Any of these, for instance, and I'm sure that you could come up with others. Depending on your preferences and the task at hand, you might weigh one of these factors more heavily than another at any given point in time. The best choice for one task is not the best choice for another. Our choice for best programming language to write the indexer for a Google search, I think, is fairly logical. And a professor's choice of what language to teach CS1 in may also be logical. And those don't have to be the same result, right? Best depends on context. Best depends on your metrics.
For example, I think this talk is best because this talk has the maximum number of Googlers up on the stage. My metrics, it's best. Do we even work together?
Rarely.
Okay, just checking.
West Coast, East Coast. Unfortunately, when it comes to best, programmers are fundamentally bad about this question, right? So, an example in 3 parts. Thank you, Twitter. Hey, I'm an artist and I use watercolors.
That's cool. I use oil paint.
Lovely.
Oh, I play guitar.
Awesome. I'm a drummer. We should jam together sometime. I'm a programmer. I use React.
Angular is the best, and I will effing fight you. Where do you live? I'm coming for you.
Thank you, Programming Twitter. Also, reminder for everyone, code of conduct. Second reminder, be good, Chandler. Don't be that Chandler.
Sorry. Good Chandler, Okay, I'll be good.
So for everyone that is expecting us, allegedly a pair of C++ experts, to say C++ is best, of course, we have news for you. Slow your roll, brace yourself for some nuance. Because really asking what programming language is best is asking a silly question. It is a lot like asking what is the best car.
Tesla.
West Coast. The question is meaningless. Best is not universal, right? We have to account for context and requirements. The right tool for one job may not be the right tool for another job. And that comparison is critical because a programming language is a tool. We have multiple programming languages in the industry, and they are well suited to different tasks, just as we have many variations on other types of tools. If you saw Chandler's talk earlier in the week, you know that there are different kinds of hammers, just as there are different kinds of wrenches and saws. Since I did the first draft of these slides, we're doing saws today. I particularly like the comparison to saws because there is a seemingly infinite variation in the design, purpose, and usage for something that could be all just described as this will cut through some material via abrasion. We have coping saws for fine detail work, or cross-cut saws for 2 lumberjacks to take down a tree.
Lumberjacks.
We have hand saws and power saws. There are saws for craftspeople and saws for bulk work. Some saws have infrastructure to them. It reminds me, in fact, of one of my favorite, slightly too long, bear with me, passages from Neil Stephenson's Cryptonomicon.
It's story time.
Story time with Titus. Now, when Bobby Shafto had gone to high school, he'd been slotted into a vocational track and ended up taking a lot of shop classes. A certain amount of his time was therefore naturally devoted to sawing large pieces of wood into smaller pieces. Numerous saws were available in the shop for that purpose, some better than others. A sawing job that would just be ridiculously hard and lengthy using a handsaw would be accomplished with a power saw. Likewise, certain cuts and materials would cause the smaller power saws to overheat or seize up altogether, and therefore called for larger power saws. But even with the biggest power saw in the shop, Bobby Shafto always got the sense that he was imposing some kind of stress on the machine. It would slow down when the blade contracted the material, it would vibrate, it would heat up, and if you pushed the material through too fast, it would threaten to jam. But then, one summer, he worked in a mill where they had a bandsaw. The bandsaw, its supply of blades, its spare parts, maintenance supplies, special tools, and manuals occupied a whole room. It was the only tool he had ever seen with infrastructure. It was the size of a car. The two wheels that drove the blade were giant 8-spoked things that looked to have been salvaged from steam locomotives. Its blades had to be manufactured from long rolls of blade stuff by unreeling half a mile of toothed ribbon, cutting it off, and carefully welding the cut ends together in a loop. When you hit the power switch, nothing would happen for a little while except a subsonic vibration would slowly rise up out of the earth, as if a freight train was approaching from far away, and finally the blade would begin to move, building speed slowly but inexorably until the teeth disappeared, and it became a bolt of pure hellish energy, stretched taut between the table and the machinery above it. Anecdotes about accidents involving the bandsaw were told in hushed voices and not usually commingled with other industrial accident anecdotes. Anyone think about programming languages right now? Jokes aside, there are some differences between saws and programming languages. I know, shock, right? When you're looking at saws, you can tell at a glance some things about them. You can look at this, and you probably have a sense that this is for detail work and isn't the type of thing you should pull off the wall if you want to cut a car in half. Whereas when you see a picture like this, you instinctually have a different sense that this might be good for something else, say, milling lumber. Different tools have different affordances. The design of the thing naturally affects our understanding of what it is useful for. Physicality of design helps us reach for the right tool for a task without necessarily relying on being told by an expert.
This is where the metaphor around tools versus programming languages starts to break down. You see, programming languages, at least the ones that I get to use, they don't really have handles or buttons or guards or things you actually physically hold.
They used to come in boxes.
They used to come in boxes, but the boxes didn't reflect what the programming language did. And this has a harsh side effect. It means that if you're holding it wrong, there's nothing about the tool that kind of gives you a sense, oh, why am I holding the chainsaw with 2 fingers? Maybe that's dangerous. It doesn't give you any reason to think about what is this going to be good for or bad at. And this gets even worse when you think about how that programming language is going to be used over a long period of time. We're not interested just in writing software once, but in maintaining it over a long period of time, and glancing at a programming language briefly isn't going to tell you how this programming language will really behave and allow you to develop software over years or even decades. Consider the Go programming language, which was designed specifically for the use case of large-scale software systems. Despite everyone working on it thinking about this reality, they forgot to put in a fundamental feature to allow it to scale well, type aliases, and they had to add that later.
That was my fault.
Also, that was Titus' fault. So, this is a bit weird. Don't get ahead of us. It's your fault.
Yeah, I know.
So this is a little bit tricky, right? When we try and classify programming languages, we end up doing so in a really weird way. We do so very coarsely. We may think about programming languages, front-end programming languages good at UI or web frameworks, or back-end multi-threaded server programming languages. We might think about whether they are compiled or interpreted, whether they're statically typed or dynamically typed. These are good categorizations, but they're very coarse. They're large buckets. Within any one of these, we don't have these nuanced senses of what the language is optimizing for. Is it, trying to give you good performance or a UI design? Do you prototype your software in this? How's it going to work over time if you evolve that software for 2 decades? What happens when new programming paradigms come out, or we get new hardware in our data centers? Will we be able to utilize it effectively? Is there a library ecosystem for it? All of these nuances are lost because we can't tell at a glance what they're going to do with a particular programming language. Ultimately, we end up treating C++ like other programming languages, and that doesn't go well most of the time, because C++ is a different programming language, and these differences actually matter to users. We really should be thinking, what kind of warning signs or guidelines do we need to put on the tin of the programming language, or the box of the programming language, in order for us to use the programming language well to solve the problems the language is good at solving? And that kind of brings us to, what is important to C++? What is different about C++ compared to all of the other languages that are in the same large bucket as C++?
So if you ask a committee member this question, what is C++? Most of us, not uniformly, but most of us will almost certainly talk about performance, and that's certainly what I've heard from most of you this week. We'll toss around terms like you do not pay for what you do not use, and leave no room for a more efficient language between us and the hardware. And that has been a great thing for the committee to focus on. It has given us a single-mindedness that has served the language very well. But in practice, it is also, it is more than a language just about performance. A lot of what matters, not just to language nerds and committee people, is the technical legacy and the general C ecosystem. We share tools and build systems and bits of language dialect with C, and that has shaped C++ quite a bit, maybe more than we usually admit. We can go into the rest of the points on this list, which are all important in their own right, but really C++ traces its roots to those top 2 things primarily. Focus on performance, for the most part, and piggyback on C. I'll dig in a little bit to these legacies. Aside from those high-level descriptors, C++ is specifically unusual because of its technical details and how it shares with C. Especially the legacy of separate compilation and linkage, the inherent binary distribution model from C, and the compatibility model that stems from both of those things. Remember, in order to bootstrap tool support and language usage back in the early days, C++ was built purely as an extension to C, as a pre-processing transpilation step. Anywhere that C objects, libraries, or binary outputs were okay, C++ was automatically available and relevant. That choice was absolutely critical to the adoption and success of C++ as a language. But it can also be seen as the source of some major and deeply startling features of the language and the ecosystem. Probably the single biggest surprise for scholars of the language when comparing to other programming languages is the fact that C++ has specification for things that are ill-formed, no diagnostic required, NDR. That means the standard specifically calls such a scenario ill-formed, meaning it is not a valid program. But since diagnosing that particular scenario may be impossible, or at least computationally infeasible, with the legacy of separate compilation and linkage, your toolchain is allowed to ignore the ill-formedness and keep on going. I'll say that in smaller words. This is a language that has false positives for the question, was this a program? This is a language that has false positives for the question, is this a program? That is a novel failure mode for compiled languages, as far as I know. I think it's a novel failure mode even for interpreted languages, because you might argue that an interpreted language might start up fine with nonsense in your input buffer, but the interpreter will at least notice when you start failing to parse. That's not what we're talking about here, right? When you have these types of ill-formed NDR problems, there is absolutely zero indication that something has gone wrong. The standard says it is not a program, And yet, you have been gifted with a shiny new binary. It will do something. It might even be one of the set of things that you think is reasonable out of the set of things that are conflicting. Maybe. Most of the time, it will be somewhat sensible behavior until it isn't, and then, statistically speaking, you won't be able to debug it. By far, the most common form of this comes from the one definition rule, ODR, and related concerns. In C++, the one definition rule states, only one definition of any variable, function, class template, enumeration type, concept, or template is allowed in any one compiled file, any translation unit, any single invocation of the compiler. And I think I'll just leave it at that, and we'll look at the example here.
So let's dig into a little bit of how the separate compilation model really works in a fundamental way and why it causes us so many problems. So this all comes from C, and the idea here is that we want to compile bar.cc and foo.cc in parallel. And the best way to do that in parallel is with something called data parallelism. It's really efficient, gives us fantastic throughput in compilation, but it requires us to provide some common inputs to both of those compilations, in the case of C, a header file, foo.h, that is the same for each one of them, so that each of these parallel systems can translate the code into executables in the same way. And that's really the fundamental issue with separate compilation. These inputs to the compilation have to match exactly. Otherwise, a definition in one may not match a definition in the other, and you don't have that one definition, you have two conflicting ones.
Okay. Pop back. And so, like, if you look at this example here, right, there is no way to put both of these things together into the same program, right? There's no way that is good ever actually satisfies the constraints, because A cannot be both 17 and 42. But your toolchain is gonna almost certainly produce a binary.
Quantum computers?
It's gonna do something, but who knows what?
Hold on. Can we solve one definition rule with quantum computers? Some kind of superposition? No, okay. So common ODR violations, ODR violations that we see programmers run into again and again look like things like inconsistent overload sets for a particular overloaded function you're calling or an operator that you're using, or code that isn't rebuilt cleanly. If you fail to rebuild one of your files and you rebuild another one after you've changed a header, the program may link. It may even start to run, but you're not going to get the results you would typically expect. We even see this more commonly with inconsistent mixtures of compiler flags or build settings between two different files. As soon as you do that, this one definition isn't the same. The inputs to these data parallel compilations aren't the same. And when you have these different inputs, there's no way for us to tell you, for the compiler to tell you you've made a mistake, because that would defeat the idea of data parallel compilation. This whole idea of separate compilation is that the two compilations don't communicate in any way. Well, if they don't communicate, they can't tell the other one that you've got a different thing than what I've got. Right? You can't resolve that. And that's what makes it so hard to diagnose these things. And that's why we have ill-formed NDR, which is basically a sign and not a cop, right? We can't actually prevent you from building an invalid program without breaking the fundamental properties of the separate compilation model. And this separate compilation thing is especially significant because of the build performance improvements it provides. We want separate compilation in order to have our builds continue scaling the way that they have in C for a long time. We're getting a little bit of help here from modules, because modules are starting to build some communication channels between the different compilations that might let us notice some of these ODR issues, some of these ill-formed NDR issues. But already, that limited communication channel we're building with modules is proving difficult for our build systems to adapt and adopt. It's proving difficult for us to keep scaling. And so we don't have an unbounded amount we can do here without undermining some of our goals, some of the things that make C++ really valuable.
In the end, we really want build performance, and we want all of the features that are necessary, even if it means that we have to trust you, the users, to do the right thing, right? But this does mean, this whole ODR issue does mean that we have a novel failure mode. And I think that in itself captures a lot of the essence of C++. we are prioritizing certain things, especially performance. And arguments of the form, well, that would be extraordinarily surprising for users, carry some weight, but are generally not the overarching objection that they might be in a different language. We prioritize performance over surprise, which is sometimes surprising. Because this is, like I keep saying, a very novel failure mode. And that reinforces for me that this is a different sort of tool than other languages, and that we really need to find somewhere to put some warning stickers, or maybe give big public talks.
That might work. So while we're talking about legacy from C, we've mentioned this ODR issue and some of the build system and separate compilation issues. We want to talk about some other things. Now, macros are kind of the favorite go-to of everyone here, but let's skip over macros. We've had a bunch of talks at CppCon in the past about macros and some of the problems they cause. Let's talk about the ABI. So the ABI is interesting. The idea of this is interesting as well. So what does ABI stand for? Application Binary Interface. This is the way that two pieces of code, once you compile them down, like two libraries, two object files, once you compile them down, how do they communicate with each other as part of the executable? That's your application's binary interface. And this whole idea comes from C and the separate compilation of C and how you linked these object files together and the libraries together. And that's interesting because the C language is an incredibly stable and compatible language. It's had stability for years. And it's also a simple language. And that's allowed it to have a stable and compatible application binary interface. Think about how simple C can be here. All you have in C is types, which are just collections of data with a very fixed and predictable layout, right? And functions. But the functions are much simpler than they are in C++. It's just the name of the function. You don't have overloads. You used to not even have inline. These were incredibly simple concepts, and it made it very easy for us to come up with this idea of an ABI that was stable and would be backwards compatible nearly forever. And C hasn't really changed as a language either. It's been a very stable language as well. So this hasn't been in tension with the C ecosystem. And that means we've had decades of people working with C, building up an expectation that their ABI existed, was well understood, and was stable and wasn't going to change. And that expectation is also something that we're inheriting into C++. But C++ is a very different language. And I think that makes all of this much more challenging.
In C++, we fight this in a different sort of way, mostly because of my old nemesis, time. Time makes C and C++ different in two subtle ways. C promises to be stable and prioritizes that above all else very explicitly. Compatibility is the overwhelming guiding principle for C. Done properly, will always have backwards compatibility. It's a lot easier to promise that, after all, when you're not promising a new programming paradigm every few years. Another way in which time impacts this is the difficulty when linking together libraries that are built at different times, possibly with different releases of the compiler or the toolchain, right? Keeping the ABI stable there faces even more time-based complexity and challenges. On top of that, types are just simpler in C, right? We just said types in C are all trivial. It's just ints and floats and structs and pointers, right? And they don't have constructors and destructors, right? That's actually somewhat critical because variables in C don't have lifetimes in the same way as objects in C++. When you don't have constructors and destructors, when you don't have a difference between the storage duration of an object and the object lifespan of the object, which are different things, and if you didn't follow that, watch some of the earlier talks this week. CJ Johnson gave a nice one on that. But when you don't have constructors and destructors, just reinterpreting the bit pattern of a piece of memory to be some other type isn't the same sort of language level no-no that it is in C++. Right? It might not be entirely portable, but you can't really break the world or break object invariants in the same way that you can with a higher level language.
And this comes with a bunch of costs, unfortunately, because of this tension between what C is prioritizing, what C++ is prioritizing. In C, the stability seems reasonable. You can assume it's all stable. We're not changing it. But in C++, we have things like complex type designs that may not have aged well, right? We have things that we want to evolve over time. But we share enough with C that we really want to assume the kind of binary stability that C provided, even though we're working in a completely different world. right? And we end up sacrificing performance for this reason. If you recall my talk from earlier this week, we talked about some of the specific performance problems we're having around unique pointer, all because we have a difficult time actually changing the binary compatibility. Some of us don't need this binary compatibility, but the language is still rooted in the C model, and that means we're still paying for it. So when you think about this inherited ABI, it's amazing to think how much is built up around it. It's not just that we base C++ on the C language, right? All of the tools in our C++ ecosystem have their roots in the C ecosystem. We use the same shared library ecosystem. We use the same linkers, the same assemblers. We use the same tools for debugging our programs. We use the same tools for doing static analysis in many cases. We do so many things, and each one of these tools can assume some amount of binary compatibility. They can even, in many cases, assume cross-language binary compatibility between C and C++. And that's really, really frustrating, right? There's nothing on the tin of C++ that would remind you, you know what? This isn't going to change too much. In fact, with C++, we have the opposite thing on the tin because we keep changing the language, right? And that's really, really alarming. And the end result for us is that most of our developers don't understand the binary compatibility problems that they're running into, right? They just aren't realizing it, and the time sneaks up on them and ends up having things change in ways they never expected.
Even further, more than just the language and execution features of what we inherited from C, we inherited the build model. At the standards meeting last February, there's a large group discussion on the interaction between C++ modules, the new C++20 feature, and existing tools, existing build tools. And I said something like, the language never promised that the output of a compiler pass would be a .o file. The fact that those pieces, that model has to change in order to adopt modules, in order to optimize build speed, shouldn't really come as a surprise, and the language definitely has a right to do that, right? It was undefined. And another participant said, even if it's true that the standards committee never promised it, POSIX did promise that for C, and that has been stable for 25 years. So of course, this is going to break the world.
And with modules, we really have started to break the world. It's cool because that means C++20 is one of the most innovating and exciting releases of C++ in a long time. We were willing to break the build model with C++20. That's amazing. But it's also a little bit concerning because all of these tools, this entire ecosystem.
A little bit, just a little bit.
Okay, just a little bit, just a little bit. This entire ecosystem is assuming that we haven't changed the build model, and now we have to update it. We're already seeing the challenges of updating build systems. But think about static analysis layers, debuggers, the stack of developer tooling, things in your IDE and your editor, all of which need to realize that we have a completely novel build model. And that's why we kind of expect modules, even though they're arriving in C++20, to have a very long tail in the adoption. This is going to be difficult for people to adopt because it's such a big change from 25 years of legacy with POSIX. And that means that we're facing an unimaginable amount of Hiram's Law dependencies.
We all knew there was going to be one of these slides, right? And in this case, it isn't even the API that is being depended upon. It's the stability and process of the artifacts involved in building and linking. Surprise, surprise. So, trolling, not troubling? In retrospect, if you build a language as an extension of an existing language using all the same tools and distribution and ecosystem, to the point that people write C/C++ as a response to what languages are you good at, then you're gonna be governed to some extent by the way that that lower level language works and what it promises, right? If people have 10 years of experience, 20 years of experience, 30 years of experience shipping a .so written in C with no problems, it's a little surprising when a C++ .so, same extension, same tools, doesn't work the same way, right? And as such, no matter what we say that we have the right to change, maybe it's too late, right? Maybe it is too late to change things. I have said before in other talks, a rolling stone gathers no moss, and stones that stop rolling gather moss. At some point, you have enough moss that it's just earth. That stone is buried. That stone is not rolling again. C++ is an old language with this magnificent burst of new momentum over the last decade, but there's no pattern for this. There's no precedent for this in languages anywhere, right? Nobody knows what this means right now. Nobody knows how to handle this going forward. Do we have enough velocity to escape the gravitational well of all of that legacy? Do we even want to? We've left everything stable for so long. What will that do to us? In theory, the members of the C++ Standards Committee have thought about all of this. We could ideally answer the question of what is C++ now and what will it be going forward by asking the committee, except obviously that's silly. Don't anthropomorphize a committee. It's not one voice, it is a collection of people.
And so with C++ 20 and the addition of modules, one thing that we're realizing is we're starting to drive this wedge between some of the legacy, some of the history of C++ and C++ going forward. As we start to do that, we have a really important opportunity. We can start really thinking, what should C++ be? If it stood on its own, if we could actually just ask for what we wanted, what would we ask for from the programming language? And so the rest of this talk is going to be our attempt to ask that question and provide some answers. But in the same way that if you ask the committee, what is C++, you won't get a unified voice. If you ask the committee or the larger community sitting out here, what should C++ be, you also won't get a unified answer, and that's okay. What we're going to present is just our perspective, especially at Google, about what we would like to have from C++ if we were able to set priorities and kind of push it in a very particular direction.
Wait, you're not king? You're not in charge?
I mean, if you want to make me king, I'm good with this. Like, do you have a crown?
I'll be right back.
Okay.
No.
Without a crown, anyways.
Let's move on.
Okay, so what are our priorities for C++? Like, what would we like to have from C++? At Google, we actually spent a bunch of time reflecting on this, and we came up with these 6 things. And we even ranked them. But when I say we ranked them, I don't want you to think this is some kind of like really rigid ordering. That's not the thing that's going on here. Most of these priorities are not in conflict most of the time. Like, typically speaking, you can get whichever things you want to get across all 6 of these. But we wanted to rank them to make it clear that, when there is a tension between them, we're probably going to resolve it in one direction. It's going to be case by case. There are going to be exceptions where this just doesn't make any sense. But overall, we expect the average to drift in this direction. And this also reflects where we think we need to be spending our time, where we need to be investing in C++ going forward. So we're going to step through all of these and talk about what they really mean to us, because these are kind of short little blurbs. They don't have a lot of detail or nuance to them, and we need to expand on that. So first up, near and dear to my heart, of course, performance-critical software. All right, before we even get into what the underlying meaning of this is, we need to get into what the words even mean, because these are very particular words that we're choosing here.
Webster's Dictionary. No, never mind.
Not quite. So performance. When we say performance here, we're not just meaning how fast is it. Yes, that is important. But it's a much more complex question than just how fast is it. We care about the latency of systems, certainly, but we also care about their throughput. And we also care about performance in different resources than just time. Time is an important resource, but it's not the only one that our software consumes. We also care about things like memory utilization. We care about binary size. This day and age, we care about battery utilization. How much power does it consume? All of these things are important ways to look at performance, and we're not trying to pick and choose which one of them. We're saying that this entire space of resource consumption is what we're talking about. The next critical word here is, well, the word critical. This means something really important. Every piece of software, of course, should go faster. I don't think many people here are like, oh no, I'm happy if my software is slower than it needs to be. That's not what we mean, right? And what we mean is that the performance is truly critical to the behavior of the software. That if your performance wasn't where it is, that would be a bug. The software might no longer serve its fundamental purpose with less performance, right? You have to have some truly critical nature to the performance before it really fits into the category we want to prioritize investment around. And this brings us to some interesting observations about performance. For us, the performance doesn't really have to do with hot inner loops, at least not when we're talking about C++. Our profiles for almost all of our performance-critical services are flat. We'll have 50 different functions at the top of the profile with only 1 or 2% of the time spent in any individual one. There isn't a hot loop we need to go and optimize. And that changes the kind of trade-offs you might want to make. It changes the kinds of things we can do with the programming language. For example, we have to have C++ be this lowest level programming language. Because when it's not one hot loop, we never have an opportunity to say like, well, I'll just rewrite that loop in like handwritten assembly or something else. That doesn't scale. We need this to actually scale out to a large body of code, and even worse than that, we need something like ambient performance. We need almost all of our code to not egregiously waste performance. And these kinds of constraints are really interesting and somewhat unique to C++.
It's as if we needed like our hash tables to be super fast. The next major bullet point here is that we need to support software evolution. We need to support long-lived software ecosystems, support the evolution of those systems, the maintenance of those systems. We need to support refactoring, testing, code visibility, component isolation, a balance between more expressive abstractions and the necessity to change things over time. Go watch my video from Tuesday. Fundamentally, we have a pretty good idea of how to do this with C++, and C++ does a better job of this than any other language that I've ever touched. So we're doing pretty well there as far as maintaining software that's written in the language. But what about the language itself? Supporting a language for decades means that I would argue that the language needs to evolve as well as the code written in the language. Language designers make mistakes too.
No.
And when we identify those, we need the means to fix them. If we don't have very well-defined and strictly enforced epochs, like Vittorio has been suggesting lately, then being backward compatible with the previous release becomes, in fact, an infinite regressing sequence of overlapping compatibility windows, and we can never change anything. I regularly get arguments raised at the committee of, we can't change that, someone wrote that code 20 years ago. And it's nice that they don't have to change that, but they get the upgrade for free, and the rest of us get a worse API. I'm not entirely happy with that trade-off. The reason that I talk about things like live at head and live at head for both libraries and languages is that I firmly believe that a series of small migrations constantly eating your vegetables is a good way to balance the expense of change versus the ability to evolve. Unsurprisingly, next bullet, we also want C++ to have good ergonomics as a programming language. It needs to be easy to read, understand, and write. This should be the least surprising of our goals. But there are some interesting points worth mentioning here. We consistently want to prioritize reading and understanding code over writing code. Most people that you hear speak will talk about how code is going to be written once, or maybe twice, I guess, and read many, 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 many more times than that. Right? While writing is still, of course, important, reading and understanding are an order of magnitude more important. For example, this often motivates Google's positions on the committee and our desire for explicit syntax. It isn't the explicit syntax that is the goal here. Readability is. Give me some hook so that I can cognitively understand what context I am in. And when we talk about reading code, it is very important for us especially to think about the scenario, the nightmare scenario, right? There's an outage, search is down, and SRE is browsing through all of the recently changed code to see what could potentially have been the problem, right? If the reader is not an expert in the language, if they are not deeply familiar with all of the systems, if they can't read the surrounding code and lack context, that's going to make that task worse. That's going to hurt us a lot. We need the code to be readable and understandable rapidly by non-experts constantly.
We also want to try and simplify C++. This is, I think, one of the really great opportunities we have to improve C++ because the complexity of the language is really holding back C++ programmers right now. I had a really wonderful exchange on Twitter. It started off with this wonderful observation that someone asked a question about R-value references. Now, R-value references are a complicated, subtle part of the language. Absolutely. But what they found, it just really scared me because it says that almost no C++ programmers they talked to fully understood how C++ worked. And even worse, the ones that thought they did were the most likely to be wrong. And that means that as a community, we struggle to understand complex but important parts of our language.
For instance, I have almost never interviewed a candidate that actually understood how copies work in the language, right? That's a horrifying thought.
And so I pointed out, this is an accurate view, and this is widespread. This isn't just this one example. This is a fundamental problem that C++ is facing. And then John Carmack summed up my point for me better than I could. He points out that one of the real advantages that C had is that a developer with enough experience, who's like really familiar with C, would probably be capable of sitting down and writing their own C compiler. Now, I don't think he means sitting down and writing like a production quality, just excellent C compiler, and I doubt he expects this to take 2 weeks. That's not the point here. The point here is that someone with a lot of C experience can sit down and over a long period of time and with a lot of effort and research, put together at least a barely functioning C compiler, and that reflects how well they understand this language. They understood C well enough to figure out how to get through it when compiling it. And we don't think many people can do that with C++ today. They don't have any realistic ability to understand C++ that well. How many folks here think they could build even the most basic C++ compiler in a year if they needed to? Any hands? Mine does not go up, for the record.
I see two.
Is
I
Richard
recognize them
raising
both.
his hand?
Yes.
That just doesn't count.
Yeah, Richard's raising his hand.
Okay.
Yeah.
And I think this is actually a failing of the language. The language should actually enable this kind of thing. It shouldn't hold people back from having a deep understanding. And this, by the way, is also not to say that you should all go and write your own compiler. I don't think that's a good use of time. What I'm saying is that you should be able to, that you should have the ability to learn enough about C++ to understand it at that depth. So with that, we're going to move to another one of our fundamental priorities for C++, practical safety and testing. Now, C++ has been doing a great job of moving towards safer and safer interfaces and APIs over the years. Spans bounds checking is one that I'm particularly fond of. There really are a lot of great things we're doing here. We have to keep it up. But I want to talk about a couple of areas where we need to push much further within the language. The first one is around security mitigations. As long as this language is not 100% safe, and I mean 100% safe, not 99%, right? If we don't go that last little bit of language safety, I think it is absolutely necessary that we provide tools that work with the programming language to provide security mitigations for whatever remains. Otherwise, people using C++, whose software ends up being used in critically at-risk surfaces, places where attacks really happen and matter a lot, won't have the fundamental tools they need to make their code secure and safe, to make their software secure and safe.
What was your talk on last year?
I feel like my talk was on this like really scary security thing, like Spectre-y almost. We also need to have better testing methodology. Now, I'm not actually talking about writing tests very much. I think the community is doing a fantastic job of adopting testing as a fundamental requirement of writing software. Wonderful job. Please keep it up. But now we need to look at how we make that a more robust methodology. We need to look at continuous integration of all of the tests that you've written so that they're running constantly on every change. We need to connect that continuous integration with checked build modes and other things like sanitizers that provide much, much greater checking of whether you have a bug in your code.
And that's hard to do when we're depending on the ABI.
And the ABI makes this much harder than it would be. And so this is an area where we think the language could also make it easier for all of you to get this kind of advantage. Last but definitively not least, we have to continue to adopt fuzz testing. This tweet really sums it up. Coverage-directed fuzz testing combined with checked builds like sanitizers is a superpower for finding bugs. If you are writing software that is handling untrusted data of any form, and you are not fuzz testing the interface that reads that data, you are not writing responsible software, okay? It's absolutely critical that you fuzz test every single layer of your software that handles untrusted inputs.
Network inputs?
All untrusted inputs. Network inputs.
Hard drive inputs?
Hard drive inputs.
User inputs?
All of them.
How's about your front end to your compiler?
We are trying so hard to fuzz test it. But do you remember those slides about the complexity? Yeah.
Yeah. We need, of course, your builds to be faster, right? We need, of course, to improve your ability to write and depend on, pre-existing code. We need just to improve the development velocity. And C++20 is going to be a huge step forward here, so long as you all can deploy modules. It is going to be a significant improvement in isolation between libraries, reduces the reach of the preprocessor macros, improves encapsulation. I suspect we'll see significant reductions in incompatibility to distance and make it much easier for us to have package management ecosystems. We'll definitely get better mechanisms for hiding internal implementations of things, give the library developers better ability to iterate on things that are not supposed to be public without all of this Hiram's Law nonsense, well, with less Hiram's Law nonsense. And that's going to make a lot of things much easier for the library authors, which will give you better quality, faster APIs, all of those things. And for all of you, also major build speed improvements, especially in code bases or projects that have deep dependency trees. This is a great step.
So the last thing we want to mention is support for hardware, operating systems, and environments. And this really is a place where C++ already excels. Because we're not just talking about, can I run my code on your fancy hardware? That's not the thing that's interesting for C++. For C++, the question is, do I have direct access to your fancy hardware? Can I get at all of the functionality of your hardware, the operating system, whatever the runtime environment is? And C++ is great at that. And this is going to be very important for today's hardware, but also going forward as we get new and exciting hardware in the future. There's one area we kind of want to pull back from a little bit, and that's historical hardware support.
So for instance, which is more important? Consistent, efficient support across all platforms for all time, or maximal ability to use the newest features efficiently on new hardware, because the hardware ecosystem evolves. Consider a recent committee discussion in my room. Should we make types like atomic signed lock-free mandatory, even though some hardware from the late 90s is lacking the necessary instructions, some atomic compare exchange machinery? Or do we delay the addition of those features because they can't be supported on 20-year-old platforms? Right? This is past versus future in a nutshell, once again, and the committee does not have a firm policy on what actually are we targeting, what do we support. Right? In this particular instance, we chose future, and therefore some older platforms won't be able to provide a fully conforming C++ implementation as a result. I think we need to define what we're committing to support and keep that rolling forward in a predictable fashion. We're not going to go out of our way to break your 20-year-old platform, but we may not go out of our way to keep supporting it either. So in the end, we've talked a lot about ecosystem pieces. What kind of a tool are we actually holding here? And I'd say what we have is a very complicated and nuanced tool with 3 unparalleled use cases. This is a language that attempts to leave no room for a higher performance language between it and the hardware. You will get efficiency. You will get performance. It is also a language that is usable on all sorts of platforms with low overhead access to C, which we should all recognize is the de facto standard native platform API. This means you get reach to all sorts of new platforms. And if you work at it, the code that you write once will basically work on all sorts of platforms and be high performance everywhere, and with minimal effort, or maybe 0 effort in theory, may last for decades. This makes it an odd tool. It has distinctly different affordances than what you find for other programming languages. It's everywhere. It's got more history than any other common language out there except C. It's done a good job of maintaining compatibility with C, and a better than average job of maintaining compatibility with earlier versions of itself. But it is running up into an identity crisis. By saying that performance is the top priority, but providing such stability, we've made it easy for everyone to depend on that stability, intentionally or otherwise. And in places where stability and performance are in tension, C++ is currently saying one thing and then doing another. At some point, that tension needs to resolve. We'll have to pick, as a committee and as a community, whether this is a language about performance or about stability. And I increasingly suspect that it is actually about stability. Our legacy and our overlap with C shows up in some of the biggest oddities for C++, the things that I wish we had warning labels for. Separate compilation and linking in a simple language like C basically makes sense. With a higher level language populated with templates, objects with lifetime, OO paradigms, we get ODR and ABI manifesting in new and surprising ways. I find it particularly surprising that we have a language that allows false positives on, is this a program?
So, despite the fact that that seems to be an accurate summary of where C++ is today, I keep wondering, where would we like it to go? And in some cases, this really would be a change of direction for C++. If we want to prioritize performance over stability, that may well be a change for C++. Personally, I think it would be a very positive change for C++, and I think it's the right direction for the language as a whole. But we need to figure out what the community wants and what direction the community as a whole is most comfortable with. That said, here's what we would like. We would like to see C++ pursue these things going forward.
Come talk to us about these afterwards. So what is C++? It is an unusual programming language. Thank you, Hannah. With some highly unusual sharp edges and risky features. At a glance, you may not realize exactly what it is capable of or how best to use it. It is also an extraordinarily powerful industrial tool that can do things that few other languages can manage. But it does require an extensive safety manual to use it properly.
And a pilot's license.
And a pilot's license, apparently. There are more sharp bits in surprising places than you might expect if you treat this just like every other programming language you've ever seen. If you treat it with respect, if you come at it from a place of knowledge, in return, we will give you as much performance and stability in some ratio as we possibly can. You just have to know how to use it if you want to keep your fingers or your power lines. Thank you.
Thank you, everybody. We have
to the microphones.
You have microphones, please. Questions.
So, evidently, C++ prioritizes stability quite a bit, and the community spent quite a long time and a lot of energy and to make sure that we have stability, and we do prioritize stability over performance and simplicity. At the other end of the spectrum, people use C++ 98 or 11 because somewhere along the way that stability is lost, or people don't believe that stability exists. So how do you reconcile that divide? And don't you think that stability ultimately is a lie, and maybe what we should go after is flexibility?
To some extent, stability is a lie. Like, anyone that has upgraded their compiler, which is allegedly a free operation, understands that, nope, not even the thing that didn't change any interfaces is free. Again, there's Hiram's law and a million other things.
That said, like you were mentioning the C++ 98 to C++ 11 transition as one which did not have stability. And yet, if you look at what, especially the GCC and libstd C++ community did in order to allow a certain measure of stability across that transition, it appears to have been a tremendous priority and also fairly effective. For me, surprisingly effective. So in some senses, yes, there have been breakages. We can't be 100% stable, but we also seem to be, to my mind, surprisingly good at it.
Hey guys, thank you for the talk. It was really educational and entertaining. Really like the format of the speakers, so maybe going forward it may be more. My question is, for me as someone who is not very familiar with compilers and development of compilers, it seems like a simple solution for this is to just add compatibility flag, right? If we want, we enable breaking compatibility mode, we build whole the system for us with all new shiny ABI and all the features. If we enable this flag, we are basically in all mode. So at a glance, why this is not that trivial as it seems?
How do you use that flag for one part of your system? You don't use the compatibility flag for the other part. How do you link them together?
They don't work together. They work only on the projects that are fully supported by a new language.
I mean, my heart is with you. I find all of our like mixed mode build nonsense. It's just nonsense. Like, there's no way we can actually keep that working forever. Like, so to some extent, yes.
I think, though, that this is the tension we have. If you have to take your entire project and move it to the new thing, right, then even one component not being ready can hold the entire project back. And if every project manages to have one component that isn't ready, then nothing moves forward. And I think that risk of failure to advance is one of the things that motivates, especially on the committee, people to desire this hard break between old and new. Because they want to ensure that new actually gets adopted. And I am sympathetic to that. I don't think that the current approach will necessarily continue to work. I think we'll have to increasingly prioritize stability to continue to make our approach work. But I do understand why it's an appealing approach if we can do it.
Thank you.
Hi. I want to touch a bit on if you're thinking about the future of C++, we're going to have to deal with the fact that C++ needs to be more teachable. And dare I say it, maybe C++ is the first language for many
don't dare.
So is this a priority for our community? For example, if we think about contrasting with other programming languages that are making this a priority in being easy to teach and having a strong presence not only in unis but in at younger ages for kids?
I think C++ should be taught, but I have a PhD in computer science education, and this is not how you teach CS1. In fact, there's 25 years worth of research on how to teach CS1, and I encourage everyone to not have any opinions until they've done the reading. It's kind of like security. I think there is a lot of room for us to do better at making it teachable and improve the quality of C++ teaching in university, so long as we are not talking about it being a CS1 thing. First, people have to get over the hurdle of being an algorithmic thinker, and then we can give them a language that has these sharp edges, right? Don't give your 3-year-old your knife set.
Yeah, okay.
Yeah.
But don't you think we should make it a priority to be, after we have all the bases and fundamentals of CS 101, make it a language that is more easily teachable?
I think
if it's not in, this is not on screen anymore. If
Yeah.
it's not in conflict with the other priorities, then yes, but most of the time, like performance is gonna beat that.
Okay.
That said, I don't think it is in conflict, right? If we can make things simple and easy, I think we will have numerous opportunities to make it more teachable at the same time. We don't have to give up on teachability, even if it's not applicable in CS 101. We can still make it much, much easier to learn and understand.
Okay, thank you.
Time for one more.
One more, last question.
Okay, so as we deprecate and eventually remove old features like order pointer, how do you judge the cost of breaking backward stability and compatibility?
Historically, we haven't. We've removed things when we thought there was an easy replacement, but that was not based on evidence. Ask me sometime about C++ 17 and random shuffle.
Yeah, we are still figuring out how to do that, I think.
Okay, so for currently there's no evidence supporting those. Okay.
Not much. Thank you all very much.
Thank you so much.